The origin and composition of slag in modern blast furnace. Hello everyone and welcome. Today we are diving into crucial yet often overlooked component of blast furnace iron making process, slag. Slag is not just a waste product. It's a vital co-product formed upon the melting of iron ore and collecting in hearth along with the hot metal. It's a liquid, but significantly less dense than hot metal, about 2.3 tons per cubic meter compared to hot metal 7.2 tons per cubic meter. The careful design of its chemistry is essential, impacting everything from its melting temperature and fluidity to its ability to desulfurize the iron and remove undesirable elements like alkalis. So we'll explore exactly where this slag comes from and why understanding its origin is key to efficient and stable blast furnace operation. Now coming to our this slag forming components, that is the gangue inputs, and here we can say that the primary source of slag is the gangue material found within our ferrous material. That's our iron bearing raw material. These include first lump ore, natural iron rich material that contain acidic gangue components like Na2O or SiO2 or L2O3. Second, sinter and pellet, which are agglomerated materials, and their composition are artificially designed by adding fluxes during their production. Think limestone, dolo, or olivine. These additives precondition the slag properties even before they enter the furnace. The quality of this ferrous burden is paramount, while beneficial at that mine aim to reduce gangue. Some is actually necessary. For example, for proper sinter quality, operators would not typically go below 3.5% silica in their sinter, with 4.5 to 5.5% being more common. A mere 1% increase in silica in the body can increase slag volume by 40 to 50 kg per ton of hot metal, showcasing the significant impact of this initial input. Now coming to our next slide, which is all about a major slag forming components. This is basically the gang inputs. So beyond ferrous burden, significant slag components arise from fuels we use as coke is gasified. Its ash primarily consists of acidic silica and alumina blend into forming a slag. So auxiliary reductant also contribute. Pulverized coal injection or PCI is a major source. Coal ash typically contain about 50% silica. Highest content in injected coal necessitates adjustment, usually a higher primary slag basicity to maintain fluidity. In contrast, natural gas injection is a unique because it contains no ash, thus contributing no slag forming components and leading to a lower primary slag basicity. And these as contribution directly influence the total slag volume, basicity, and liquidus temperature, making a fuel selection a critical consideration for slag management. Now, the actual formation of slag is a journey within the furnace. It begins in the cohesive zone at temperature of around 1200 1400 degrees centigrade band where burden materials soften and collapse. Here, primary slag form a mixture of gangue from the ferrous burden with significant amount of oxide or FeO. As the primary melt descend and heat further, FeO is progressively reduced out, which tend to increase the slag liquidus temperature. Simultaneously, ash from coke and injected fuel generated at various elevations blend into this melt. Even at the 2 year where coke and coal are gasified, some slag component are produced around 32 kg per ton of hot metal in a reference furnace. The final hot metal and slag composition we tap are the result of this complex iron slag interaction and the blending of various liquids within the hearth. The four main constituents that we need to aid in memory, that CaO, SiO2, Al2O3 and MgO, collectively make up about 96% of total slag volume. The chemical composition and the control of slag volume, let's discuss about these. So let's look a closer at major slag constituent crucial for effective control. Calcium oxide, typically it's 34% to 42%, is a primary basic flux, uh, essential for desired slag basicity and effective desulfurization. Silicon dioxide, 28 to 30%, is the main acidic component from the gangue and the ash. Remember, a 1% increase in silica in the body can boost slag volume by 40 to 50 kg per ton hot metal. Alumina oxide, 8 to 20% also from the gangue and ash. Even somewhere it looks more 21, 22% even. Level above 18 to 20% are generally undesirable due to increased viscosity. Magnesium oxide, 6 to 12% from fluxes like dolo or olivine, maintaining 8 to 11% is often preferred for stable furnace operation. We use basicity ratio like B2, that is CO by SiO2, or B3 CO plus MgO by SiO2 to precisely tailor slag properties. A lower slag volume such as the 250 kg per ton of hot metal in our reference furnace is consistently desired. These directly translate to enhanced productivity and reduced heat requirement for melting. Ultimately, the quality of raw material, their gangue and ash content dictate the achievable slag volume, making careful selection paramount. Now, coming to a very important area of the slag properties, which have a profound operational impact. Its liquidus temperature is critical, governing fluidity and its ability to efficiently drain from the hearth. Higher liquidus temperature mean thicker, more viscous slag, uh, uh, and during thermal upset like a coal furnace, we might reduce slag basicity by 10 to 20%. This we have to remember as a fundamental standard operating practice. We have to reduce the slag basicity by 10 to 20% by adding siliceous lampor to lower its liquidus and maintain fluidity. Slag is also the primary medium for desulfurization hot metal with effectiveness depending on its basicity and temperature. Furthermore, slag is the main route for removing problematic element like alkali, that is primarily sodium and potassium. And in my past presentation I have also shown that this potassium is more preferred compared to sodium as far the impact and the detrimental effect is concerned. We need to more focus on the potassium and even some zinc from the furnace. Crucially, higher slag volume generally decrease furnace productivity. This is because more energy is consumed to melt and process the additional slag. So for every 10 kg per ton hot metal increase in slag rate, productivity can decrease by 0.05 tons per cubic meter of inner volume per 24 hours. So strategic slag management is therefore directly linked to overall furnace performance and efficiency, and we supposed to is the most important activity. Now coming to the conclusion, we can say that we can mention that the slag is very important phenomena which need to address very correctly. Otherwise we will have a problems. We can show that more input will hamper the process very drastically, and which leads to a decrease in production and productivity. And we can say that in conclusion, blast furnace slag is a complex multi-component material originating from gangue in the iron ore, sinter and pellet and lump that we have already seen, and the ash from the coke and the injected fuel like coal and oil. Effective slag management is not about eliminating it, but also meticulous control its volume and chemistry. This requires careful raw material selection, precise burden calculation, and dynamic operational adjustment, such as basicity tuning and managing injectant, ultimately achieving an optimal lower slag volume or desirable chemical properties directly leads to enhanced productivity and reduced fuel rates, and also lower environmental footprint. So a deep know why of slag formation and behavior is therefore indispensable for modern sustainable iron making.